Okay, hello everyone. My name is Zbigniew Skowron, and I will talk today about using exceptions in C++. I will talk about a few practical things, but this will definitely not be a complete guide. So let's get started. So first, the motivation. Why do we need exceptions? Because we need rich error messages. When we are using error codes for reporting errors, the channel for transferring information about an error is very narrow. It's like an int, maybe 2 ints usually. And also, most of the time, the error codes describe errors in a very generic way, like efail or einval or eperm. They just don't say a lot. So the primary problem is that there is no information about context. When your application will tell you that there was a permission denied, you don't know like to which resource the permission was denied, what permission was missing, and why the application wanted this resource in the first place. So basically, you can't really do anything with such a little amount of information. Another problem with error codes is that as they travel through your program, they really lose a lot of information. If operating system returned some error code that was maybe kind of specific, then probably afterwards it traveled through some third-party library that you are using, and it was converted into some error codes of this library, and then it entered your application and it was converted into your error codes, and then it was used in a function that only returns as an error can only return a null pointer. So from an error pointer, you get only, true, false. So when the user finally gets to see a problem, he sees only an unknown error or something equally insignificant. So we really need richer and very detailed error messages. Let's look at the typical code in C. So in C, we don't have anything to help us with errors, with dealing with errors. So after every function, we manually check the error code. We manually perform cleanup actions. And this code is duplicated in many places, and it's very easy to make mistake. It's very easy to forget something. It's very easy to add something that shouldn't be there because we're copy-pasting code all over. So this is a maintenance nightmare. Also, it is very easy to ignore errors because you forgot to handle something. But the biggest problem is that the whole application logic is completely obscured by this cleanup and error handling. Most of the code in your functions is cleanup and error handling, and it's not doing anything that actually adds any value. So this is a problem. In C++, we can, of course, use exceptions and destructors for cleanup. So when we do that, our code suddenly contains only code that actually does something useful. We get rid of all the error handling and all the cleanup. It's not even there. So it's much easier to maintain, much easier to understand, but most importantly, in this case, all errors are handled correctly, and all resources are freed without our intervention. we don't even have the ability to break it because the compiler generates that for us. So if you're like me, you first encountered exceptions by programming in Java. And in Java, error handling is really messy, just as in other garbage-collected languages. Because whenever you need to ensure that some resource will be freed, no matter if a function will return with a success or with an error, you have to insert manual error handling using a finally block or a try with resources statement. But it's still manual work that obfuscates your code. Even worse is the problem that in Java still checked exceptions are quite popular. So checked exceptions are about declaring which exceptions your function can throw. And result of that is that a lot of code in Java is simply catching errors and rethrowing different type of exception just because the type doesn't match. So this really obfuscates the code, and we really don't want any of that in C++. So fortunately, we have deterministic destruction in C++. So that means that all the destructors are called automatically by the compiler, regardless of whether the function exits with a success or through an exception. And deterministically, so all destructors are called at a very specific time in a very specific order. So actually, this makes C++ much better suited for using exceptions than garbage-collected languages, where you don't have those properties. So you should use destructors for cleanup everywhere. And they are also critical for writing exception-safe code. Of course, as with everything, there is a little asterisk there, but I will not go into details today. Okay, a lot of people, when they see a throw statement, they feel a bit uneasy because they don't think they really understand what is happening there. So they're a bit hesitant to use exceptions. But the thing is that a throw is almost the same thing as a return. So let's see how it works. So a return works in a really straightforward way. When we exit a function, all the local objects are destroyed in a well-defined order. And then we go back to the calling function. And when we return from the function, all its local objects are destroyed in a specific order, and so on. So what happens when we change our return below to a throw? Well, it works exactly the same. It works exactly as if it was a return, or the local objects are cleared, and we return to the calling function. So the only difference is that at one point, when we find a matching catch statement, we simply, instead of returning again to the calling function, we jump to that catch statement as if it was an if that was checking an error code. So you shouldn't be afraid of a throw statement, because if you know how return works, you know how throw works. There is no magic there. So there is one catch, however. You shouldn't throw from destructors. And why is that? So when we throw an exception from a function, then we destroy local objects. And if during destruction of an object, another exception will be generated, then we would have a problem. We would have two exceptions trying to fly at the same time. And what would we do with them? If they would reach a catch statement, which one would be handled? The first one, the second one, both of them, none of them? So we could like answer this question differently, but C++ has its answer, and it's the simplest answer possible. It's simply not allowed. If such a thing will happen, your program will be terminated. So don't throw from destructors. Okay, however, throwing inside the destructor is okay, because when we throw inside the destructor and catch it, so that the exception will not escape the destructor, we don't have this problem. Like, we don't have two exceptions trying to reach the same catch at the same time, right? We kind of, the first exception is stopped for a moment, the second exception is generated, it is caught, and then the original exception, can resume without problems. So this is perfectly fine, and it's allowed. Okay, so what to throw and when to catch? First of all, in C++, it doesn't really matter what you throw, because you can throw anything. Standard library has a standard exception type, but this type is not special in any way. You can use your own type, an empty struct. You can use anything. The simplest usable exception in the standard library is called runtime error, and it simply takes a message. So this is a message, and it's fine. You can throw runtime error, no problem. However, what I would recommend is to use the boost exception library. And this library provides one type, boost exception. So boost exception is basically a container for data. You can put there anything you want. So whenever you have an error to report, you just create, like, preferably your own exception type, but that is deriving from a boost exception. And you just put into this exception all the information about the error you can get. You put there everything that might be useful for analyzing this problem. So you can put there name of the function that failed, error code from the operating system, file name and line number of where the exception happened. You can put there a call stack. You can put there anything you want. So you can get really rich error messages. And how to get an error message? Well, first of all, you can query this container of data programmatically, but there is also a convenience function, current exception diagnostic information, which simply gives you a string that contains all this information you have put into this exception. So this is good for logging stuff. This is good for debug information. So this is how you get rich error information. Okay, so now when to catch? There is also a simple guideline for that. You should not catch exceptions, right? Exceptions are not meant to be caught. Exceptions are meant to terminate the operation that you are doing. So we really should think about exceptions as asserts. The only difference is that asserts kill your whole program, and exceptions can kill just one operation. But you should think about them as something that aborts entire operation. So you should let them fly to the top level and catch them at the top level, and you report this error, and you go on with your life. So what is this top level? Well, it can be your main function. You can catch exceptions in main, report it, and exit or do something else. It can also be a UI layer. If an exception will propagate to the UI, you report the error to the user, a very detailed report. The user will have all the information he needs to change the environment in such a way that when he retries the operation, it will succeed then. It can also be an API boundary. For example, you can catch all exceptions at the API boundary, and for example, translate it into error codes if your API has to communicate with the outside world via error codes. So you also can do that. You can catch exceptions at the boundary of the medium, like if you need to transfer exceptions through a network or transfer it through some messaging system, you can also catch there and transfer them across. So the important thing here is that when an error happens, it is extremely rare that you have something useful to do with this error. Most of the time, you cannot do anything because retrying the operation most of the time doesn't make sense. Because why would the operation succeed the second time you do that? Assuming that would be insane. So that's why most errors are something you cannot do anything with it, and that's why they should abort the operation. However, there are some kinds of errors where it actually makes sense to retry. So those are, for example, network exceptions. Retrying a network connection is something reasonable, right? So, but this is very rare. This is an exception. Generally, you don't catch exceptions. You let them fly to the very top. Okay, so the guideline is throw generic exception. It doesn't need to have any specific type because it's just an assert. But make sure to put all the information about an error you can get into it. Create exception types only for things you actually want to catch. So this is very rare. Like I said, network exceptions are a good example of that. And don't create any Baroque exception hierarchies because they simply don't serve any purpose. So where not to throw? We already said that you cannot throw from destructors. You cannot throw from deallocation and swap also. And why is that? Because we don't know how to write programs where deallocation, destruction, or swap fails. So basically, we need those things to work, to always succeed, in order for us to be able to write programs that are reliable. So the standard library assumes that you don't throw from destructors, deallocation, and swap. So if you will violate this contract, you're in the world of undefined behavior. So don't throw from destructors. Okay, so if you can throw from destructor, and you have code in destructor that throws, what do you do? The only thing you can do is to catch the exception and ignore it. You can log it somewhere, but ultimately, you have to ignore it. There's no other way. So the question is, isn't it really bad that we are ignoring the errors? Well, it is bad, but it's not as bad as it sounds, because most of the stuff we want to do in destructors, the cleanup actions, don't throw. Other destructors don't throw. The allocation doesn't throw. Closing files doesn't throw and doesn't error. So most of the stuff that we want to put in destructors don't fail anyway. So this is not a problem. Sometimes, like in the case of RPC, when you have resource on the other side of the network, for example, it can throw. But yeah, if it will fail, there is nothing we can do about it anyway. Like, we can try to do it again and again, but ultimately, you either have to ignore it or kill your program. There is no other way. So here we have a little short function that does one thing. It promises that if it will end with a success, it will write your data to a file. So it uses this smart file object that buffers all the data that you write into it, and in its destructor, it calls flush and actually writes the data onto the disk. So where is the problem? Why there is a bug? Well, because what happens if the flush will fail? When we write data to the disk, and the operating system says, there's no room on the device. I cannot do that. So we throw in the destructor. We ignore this error because there is nothing we can do about it. And suddenly, the function exited with a success. It didn't throw an exception. And yet, the data is not on the disk. So clearly a bug, right? So why did this bug happen? Because we did, in the destructor, some part of our application logic, something that was required to fulfill the contract of the function. So we really cannot do that. We cannot put in destructors any of our application logic. We can only put there cleanup. And if a cleanup will fail, well, the function already, if we will fix the function and put the explicit flush at the end of it, then it can report errors. And if the function will finish with success, then all the data is on the disk. So now, if the cleanup in destructor, meaning if there was something that could fail, then ignoring this error wouldn't be that much of a problem because the function already did what it was supposed to do. So it fulfilled its contract. So the function worked. It can return a success. Now, if the cleanup failed, then it only means that we have some resource leak, but resource leak that we cannot do anything about anyway, because we tried, and trying it again doesn't make sense. And that it's just the universe preventing us from doing the right thing, but we cannot do anything about it. Okay, so now why doesn't C++ have finally? Because finally blocks are just ad hoc destructors, and we don't need them in C++ because we have the real destructors, automatic destructors. So we don't need finally, right? But sometimes we just want ad hoc destructors. So we can write them. We can use scope guards, and the scope guard is an object that simply takes a function and calls it in its destructor. So this way, it's useful when you are using some C libraries, for example. You have one function that creates some resource. You have another function that you need to call to release this resource. So you can use this scope guard to create this ad hoc destructor that will simply clean up the object when the function exits. But we need to remember that this is still called in destructor, so it cannot throw, it cannot fail. There are two other kinds of scope guards. One is scope success, another scope fail. And scope success also takes a function and calls it in its destructor, but calls it only if the function exits normally without an error. And scope fail does the opposite. It takes a function and calls it in its destructor only when the function exits with an exception. Right? So scope fail gets a function that cannot fail because, when we are exiting with an exception, we cannot throw another exception. So code we pass the scope fail cannot raise exceptions. So we can only put cleanup actions there. However, in case of scope success, it's called when there is no other exception active. So actually it can fail. We can put their code that throws. We can put application logic in this destructor, and it can throw. So let's get back to our smart file example. What if we would put flash in its destructor, but call it only if the function exits successfully and not if the function exits with an exception? So that would work. That would make our initial implementation of the function that writes to a file correct. We would throw from a destructor, but it would work perfectly. No problem there. So great, right? However, there is one little problem. As I said, standard library assumes that no destructors throw. So if you would attempt to put such a file, such a smart file, in a standard vector, then you would violate the constraints of the standard library. So you really cannot do that. So the thing is, you really should not throw in destructors. And there are some exceptions, like scope success, where it works. And I strongly suggest to stick with just that one idiom and don't throw from other destructors. OK, so yeah, are exceptions slow? People say often that they are very slow. So let's talk about this for a moment. First of all, usually exceptions are implemented like this. A compiler at compile time generates static tables that describe for each instruction in your code how to unwind the stack during exception, which objects to destroy, and in which order. So those tables are huge, and therefore compilers compress them by turning them into bytecode, and this bytecode is then interpreted by a virtual machine that rebuilds this information as needed when the exception is generated. Let's look a little bit at the assembly now. So here we have a very simple example code. We have a function f that returns some value, but sometimes it returns an error code, -1. Sometimes it fails. And then we have a function g that uses function f for something, right? Here we are not doing any error checking. So this code is really not too sound, but yeah, let's see how the assembly looks. And on the right side, you see there's a little bit of assembly instructions. It's very simple. There's nothing odd there, just trivial code. So let's now fix the G function to check for errors. So we add an if statement that checks for the error. And surely enough, in the assembly, we have the necessary assembly instructions that perform this check. OK, so yeah, that's not surprising. So now let's switch to using exceptions. When we use exceptions, we will change the return -1 to a throw, and we will get rid of the error checking here because it won't be necessary. So how does the assembly look then? Well, the thing is that the assembly looks exactly the same as in the first case when we didn't do any error checking. So the errors are handled correctly, just as when we were using if to check for them. So the errors are being handled. but there is no code that does it. Yeah? So when you are using exceptions, it's not only that error handling code disappears from your source code, it also disappears completely from the assembly. So are exceptions slow? Well, they are negative cost abstraction because they're actually infinitely fast. Because there is no code, so it cannot be faster than that. It takes 0 milliseconds of overhead. So where's the catch? Well, the catch is, of course, when you try to actually throw an exception. When you throw an exception, then the compiler has to load this bytecode, load this virtual machine, interpret this bytecode, figure out which objects to destroy, and this takes time. This takes a whole lot of time. So exceptions are extremely fast when there are no errors and are very slow when there are errors. So another thing is that exception handling adds a lot of this data to your program and adds a lot of data that actually performs all those operations that do the stack unwinding. But the thing is, if you use exceptions for errors that happen infrequently, they are much faster than error codes. And if you use exceptions frequently, then you're really slow. So, yeah, so are exceptions slow? It depends, right? Depends on what you use them for. So don't use exceptions for anything that happens frequently. Okay, now thread interruption. It's often that we have some background work and we want to cancel it because the user clicked a cancel button in the UI. We want to drop all the work. So yeah, how do we cancel a background thread? We cannot kill it because our program will be in undefined state. So the classic solution is to use an exit flag and check it to cancel our work. So this is very intrusive to our work. We have to put the error checking everywhere. We have to propagate it, the value of the flag. We have to then exit from whatever nested call stack we are in at the moment. And it's very difficult to make it work reliably. So what can we do about it? Well, first of all, let's think about when should we check the exit flag. Usually, it's checked when it's convenient for the programmer. So, in every loop iteration, in every function somewhere at the beginning or something like that. But it's not where we really want to check for the exit condition. We want to do it during lengthy operations. So while we are waiting for an I/O operation, while we are waiting for an event or for some timer. And the problem with that is that while we are waiting, our thread is suspended. It doesn't actually process any instructions. So we cannot check exit flag there, right? So enter boost interruption. So boost thread has a very nice feature called thread interruption, and it works like this. Every thread has a thread global exit flag and a thread global interruption event. And each function that is waiting for something, like thread join, condition variable wait, or timer, each of those functions waits for two things at once. It waits for the thing it's waiting for and for the interruption event. And how do we interrupt a thread? We call a function that sets the exit flag and then triggers the interruption event. And after that, each of those waiting functions, they wake up, they check the exit flag, and if the exit flag is set, they throw an exception. They throw boost interrupted exception, which aborts the entire operation, right? We're not catching it anywhere, it just aborts the whole thing. It really nicely cancels our whole operation. So the best thing here is that our code that we write is interruptible by default. We don't have to do anything. We don't have to change it. We don't have to do any manual checks, and it's interruptible. The only place when we have to do something is in CPU-intensive work. Then we have to manually insert interruption points. But other than that, our thread interruption just works without our intervention. Okay, so another thing is exception propagation. So very often we have some background work that can fail. So what can we do then? Well, we have to catch an exception, and we have to do something with it. So we can store it in something called exception pointer. An exception pointer is like a shared pointer to an exception. So in our background thread, we can catch this exception, store it in some variable, and then in the main thread, we can rethrow it. So that's how we can propagate errors from the background thread to our main thread. Another thing we can do is use standard future. So a future is just an object that can store either a value or an exception that prevented this value from being computed. So either a value or an exception. And future has many features, but the point is that we can wait on the future for the value of the background computation. And if the value will arrive, we will get it. And if an exception will arrive, it will be rethrown from here. So this is also a way to propagate exceptions from a background thread. Okay, another point is that C functions cannot throw. And moreover, you are not allowed to throw an exception through some C code. So when you have a C API that accepts a callback, and you put there your function, your C++ function there, you must make sure that this function does not throw. Because when it would throw, the exception would start to propagate, but the compiler wouldn't have this data that describes how to unwind the stack, how to clean up everything, because the C compiler doesn't even know about exceptions. And the C code is not written in a way that is aware of that. So you really have to catch all exceptions in your callback and then propagate them from your callback to your C++ code on the side. You cannot just throw it through C code. So for that, you can use either futures or exception pointer. Both work really nice. OK, so another place where you would want to propagate exception is where you have some different medium at some point. So for example, when you reach a point where you want to report an error somewhere remotely. So you have to propagate the exception through a network or through a messaging system, or store it into a database, and then sometimes later maybe load it back. So what can we do about it? Well, it's actually kind of tricky because exceptions, in C++ you can throw anything, but you cannot serialize anything. So you cannot just serialize the exception on one side, pass it through the network, and unserialize it on the other end. However, what you can do is to identify those exceptions that you actually want to catch on the other side and write serialization code for those few exceptions. And everything else, you just propagate as a generic exception. Make sure that when you propagate it as a generic exception, you also include all this data you have put into this exception in the first place. It can be as simple as just stringifying the data and sending it through the network as a debug string. It works for most cases. You can do more fancy stuff also, but strings work just fine in practice. So on the other side, you simply unserialize exception and rethrow it. And like I said, because we don't catch exceptions most of the time, it doesn't really matter what type they are. So this really works well for most cases. It's not ideal, but it does the job. Okay, now for another huge topic, exception safety. So what is exception safety? Exception safety are basically levels of how your code interacts with exceptions. So either your code has no throw guarantee, which basically means it does not throw, simple. It can have strong exception safety, which means that if an error will happen during execution of your function, you will either, this function will then completely roll back everything it did. So we have a transactional semantics here. Function will either succeed or be completely rolled back. There's basic exception safety. It means that when an exception will happen, the function might have already done some work. It might have been stopped in the middle of its work, but it didn't break anything. Like all the invariants are satisfied, so everything works, everything is in good, consistent state. It's just that the function did only part of its work, right? So this is basic exception safety. And no exception safety is, if an exception will happen, undefined behavior, or resource leaks, or bad things. So this means no safety, no exceptions allowed. And the funny thing about exception safety is that it is really not specific to exceptions. When you are using error codes, you really have to know about this exception safety also. That's why a lot of people are starting to call this failure safety. So this failure safety is really about specifying the invariants in your code and making sure that whenever an error will happen, however you report it, when an error will happen, you will exactly know what will be the result of your program. And that you make sure that all the invariants are satisfied and your code is not broken. So there's a lot that you can say about exceptions and exception safety, but if you're interested in that, I would like to recommend you presentations by John Kalb from CPPCon. He, in a little bit under 3 hours, discusses this topic in depth, and those are really good presentations, definitely worth your time. So thank you for listening.